So first of all, the topics of this chapter is entropy and Gibbs free energy. Okay, so of course we have to understand what is entropy and what is Gibbs free energy also. Okay, so we start from entropy. Okay, start from entropy. Yeah. Okay, so now the first point, entropy change. Entropy change. We know enthalpy change. Okay, enthalpy change. Where enthalpy change, you have endothermic, we have exothermic. So endothermic is absorbing the heat energy from the surrounding. Exothermic is release the heat energy to the surrounding, and that is enthalpy change. So over here, what is entropy? So it is the measure of the disorder of a system. Disorder of a system. Okay, so first, what is system? So system is solid, liquid, gas. So solid, liquid, and gas. So this is the example of a system. Okay, so solid change to liquid is called melting. Melting, and then when they become liquid, so you heat up the liquid, then it boils and it becomes gas. So this is something which is very basic, and let's look at the disorderity of the particles. Solid is basically they arrange in order. Then liquid is like a little bit separated. Some is still linked together and some is separated. Gas is totally separated and separated further apart. Okay, so when you go through from left to right, the disorderity increase. That means it become more and more disorder. And the concept of entropy is, if disorderity increases, then the entropy increases. Entropy increases. So we look at the disorderity, that means. Okay, what symbol we use in entropy? We use delta S. Delta S. Enthalpy change, we use delta H. Entropy change, we use delta S. Delta S, entropy change. Okay, so delta S. Okay, so delta S, the unit. How about the units? The unit is Joule per Kelvin per mole. Joule per Kelvin per mole. Okay, so of course, enthalpy change you should know, kilojoule per mole. Kilojoule per mole. This one have per Kelvin, have per Kelvin. Okay, so now let's move on. Okay, now second point, a system becomes more stable when its energy is spread out in a more disordered state. So what is that? Okay, so I give you one example. Okay, example. You heat a solid. Then the solid is not stable already because you heat it up. So the solid is not stable. So to be stable, energy is spread to a more disordered liquid state, which means melting happened. Okay, so that is what the second point talking about. So let's see it again. They said a system, let's say solid, the system is solid, become more stable when its energy is spread out. So you heat up the energy, it has extra energy, make it not stable. So the energy is spread out to a liquid, to a more disordered state. So it will remain stable as liquid state. So that is where melting process happens. So next point, spontaneous change. So a change that tends to happen naturally. That's the meaning of spontaneous change. Once started, the change will carry on. Okay, so it means what? Okay, example. So example. Okay, I put it here. Example. At room temperature and pressure, ice will spontaneously melt, but water will not spontaneously freeze because it's room temperature, right? Okay, so the property here is if it is spontaneous change, then entropy will increase. Should be reasonable, entropy is about the disorderity of a system. So this is solid, this is liquid. So solid to liquid, as we discussed before, solid to liquid, this is ordered, this is disordered. Disorderity increase, entropy increase. Okay, so now we put in one more idea. If the process is a spontaneous process, then entropy will increase. So we know two sets of idea. The first set is disorderity increase, entropy increase. The second set is spontaneous change, entropy increase. So two sets of idea. Now let's move on. Spontaneous change may not be instantaneous. That means instantaneous is like happens quickly. It can happen slowly, Okay, so or happens rapidly. Most are slow. Like the melting of ice is slow, unless you go and heat up lah. Of course, if it's at room temperature and pressure, you want the ice to melt. It just happens slowly. So most are slow and need an input of energy to start. That means it's activation energy. Okay, so natural process lah. Now 13.2, changing entropy. So let's see the information here. As a substance changes states from solid to liquid to gas. So we discussed already, solid, liquid, gas, disorderity increase, entropy increase. So its entropy increases as molecules become more disordered. So as in here, we discussed this already. So just move on. When an ionic salt is dissolved in water, ionic salt is solid. Okay, it's solid. So when you dissolve it in water, then it becomes aqueous. So the entropy increases as the crystal breaks up and the ions find their way between the water molecules. Okay, so try to imagine what happened, especially in terms of disorderity. So they are more disordered. So because of that, entropy increases when the solid dissolve in aqueous. They break down, the solids break down their ionic bonds. They are not arranged in order anymore. Then they mix around in water molecule. So the disorderity increases. Okay, next one. Increasing the temperature of a substance without changing state. That means you heat up the water, for example, but the water haven't boiled yet. You just heat up only. Increases entropy. So increases entropy also. This one, you heat up the water increase in entropy. So example, of course, disorderity increase also. You heat up the liquid, they are not as ordered as now. They are like separated further apart. Although they haven't reached the gas yet, but they are still separated further apart. So the disorderity increase also. So example, when heating a gas, the number of different possibilities for arranging the energy over the molecules increases. So likewise, if you heat up the gas become more and more disordered also. Okay, so of course they use different way to put it. They say you give the gas extra energy, then the gas you arrange in different way to use up the energy, or they said arranging the energy in different possibilities. So more or less the same. Okay, more or less the same. They put in different aspect. Now, if a reaction increases the number of gas molecules, the entropy increases. This is another example. Okay, so as gases have higher entropies than solids or liquids. So gas has higher entropies. Gas has higher entropies compared to liquid and solid. And now they put one more idea. They say if you have a reactions that increase the number of gas molecules. So maybe for example, let's say, okay, something that we are familiar with, calcium carbonate. You heat it up, then it becomes calcium oxide plus carbon dioxide. So this is a reactions that increase the number of gas. They form CO2. So of course, in this case, entropy increase. Entropy increase because gas has higher entropy. Gas has higher entropy. Yeah. So next one. Simpler substances with fewer atoms have lower entropy values than more complex substances. So in terms of disorderity, you try to imagine. So complex substances, their atoms arranged in all kind of way. So maybe like some is tetrahedral, some is trigonal planar. So some is octahedral shape, or bipyramid. Okay, all kind of shapes and all kind of disorderity. So because of that, the entropy is greater. If they are simple, then they don't have all kind of variety of structures, and then entropy is lower because it is more ordered. Okay, so next one. For similar substances, harder substances have lower entropy values. So it's related to disorderity also lah, in fact. So let's say, for example, so diamond. Diamond is just sp3. It's carbon that's extend in tetrahedral shapes only. So it is the hardest substance in the earth. So of course, according to the words here, they say it has a lower entropy values. So that should be reasonable. So because if you look at diamonds, they are disorderly. I mean, they are in order. They are arranged in order. They are just tetrahedral shape throughout the whole structures. So it's ordered. So the entropy is lower than graphite. Graphite is not as hard as diamond, obviously. Okay, so you can cut diamond. You can cut graphite. You can cut graphite. Graphite is soft. So, in terms of entropy, graphite has a higher entropy. So you can think about it by imagining. You just imagine on the structures of graphite, which is a few layers of sp2 hexagonal rings. Hexagonal rings. So it's not just hexagonal rings throughout the structures. There are layers by layers. Okay, layers by layers. That is not as ordered as diamond. So that's why graphite has higher entropy. Okay, so another fact over here: conversions of a diamond into graphite. This is a waste. Diamond is so valuable, and you convert it to graphite. This is a waste, but it's a spontaneous process at RTP. It's a spontaneous process, and this fact fulfill the information just now. Spontaneous process, spontaneous change, entropy increase. So diamond to graphite, which is spontaneous process, of course, the entropy increase. This is what we discussed also, where diamond has a lower entropy because it is harder, or because it is all 100% tetrahedral arrangement. This one has sp2 hexagonal rings, and as well as intermolecular forces. When there was intermolecular forces between layers and layers, so they have a mixtures of chemical bonds. Okay, so it's not as ordered as diamonds. Okay, now let's move on. So from here, you already know entropy change. Okay, now let's see the other side. Okay, so the other side of the note, we have 13.3. 13.3, yeah. So just now 13.1, 13.2 is about entropy. It's entropy, yeah. So entropy of a system. Okay, that is 13.1 and 13.2. Let me write down first. 13.1, 13.2 is about the delta S of a system. So just now I also explained what a system. System is basically the solid, liquid, or gas. That is a system. Okay, so it is about the reactants. Reactant is also solid, liquid, or gas, or product. Product is also solid, liquid, or gas. Okay, so that is 13.1 and 13.2. Now when we come to 13.3, right? 13.3 13.3 before we start, right? So let's see the difference first. 13.3 is about, okay, right here. 13.3 is about the delta S of the surrounding. Surrounding of the reactant and the products. Okay, imagine the reactant is in the aqueous solution, and then the surrounding is the water. Okay, it's the water. The reactant and product is the entropy of system, and then the water involves the entropy of the surrounding. Okay, so and then now let's see something that we are familiar with. For example, exothermic reactions. Exothermic reactions is, we know long time ago, this is heat releases to surrounding. So the surrounding is what? Example, water. Water is the surrounding. Okay, so if you have heat releases to the surrounding, which is water, so of course the water become disordered. So receive heat energy, right? So become water becomes more disorder, and because of that, entropy increase. The entropy here is entropy of the surrounding, not the entropy of the system, it's entropy of the surrounding. So entropy of the surrounding increases for exothermic. Okay? So I have to put something like this first, so that when you look at the notes, you can be, easier for you to take it. Okay, now let's see the information here. Exothermic reactions, energy released to surroundings, already discussed, released to the water, and then increased ways of arranging the energy of molecules in surrounding. You give energy to the water, so you increase the ways of arranging the energies of the molecules, of the water molecules. So, for example, they use the energy to increase the kinetic energy, or they use the energies for evaporation, or they use the energy for breaking up the intermolecular forces, which is hydrogen bonds. So there are many ways to arrange the energy, many ways to use the energy. Okay, so entropy increases. So the entropy here is entropy of the surrounding. Entropy of the surrounding, which is delta S surrounding. Not related to just now. Just now is delta S of the system, which is the reactant of the product. Okay, that release heat to the surrounding and increase the entropy of the surrounding. Okay, then increase probability of chemical change. Okay, so increased probability of chemical change occurring spontaneously. So that means exothermic reactions will make spontaneous chemical reactions happens with a higher chance. Okay, so yeah, hot, right? Okay, it's hot, and reactions, exothermic means release energy to the surrounding. So the surroundings is hot, and then chemical reactions can happen more easily because the surrounding is hot. Okay, so now let's see the other part. Endothermic reactions. Energy absorbed from surrounding. Decreased ways of arranging the energy. Is the opposite from this, right? So it you remember, decreased way of arranging the energy, this refers to the surrounding, the surrounding, which is the water. The water is the surrounding, for example. So the energy is taken by the system already. It's taken by the reactants or the product already. Okay, and because of that, the water has less number of ways to arrange their energy because the energy is given away to others, and because of that, entropy decreases. So it's just the other way around. Water become more ordered. They arrange more orderly, and then increase probability. This is decrease. Decrease. Typo error here. Decrease probability of chemical change occurring spontaneously. Okay, so that means because the surrounding is cold, and then chemical change could hardly happens. So, to have chemical reaction, we need activation energy, right? So if the surrounding is cold, then reaction is hard to happen. Okay, so now let's see 13.4. Calculating total entropy change. Total entropy change. Okay, so what is total entropy change? You can go straight to this point first. Total entropy change is the entropy change of the system, which is the reactant and the products, plus the entropy change of the surroundings. Logically, it's true, no? So you want to total, you have to add, right? What should you add? We just learned two types of entropy. Entropy change of the system and entropy change of the surrounding. You add up that two, then that is total entropy change. So that's why we have this. Okay, so yeah, let's see more information. Firstly, calculate the entropy change for a reactions. That is the entropy change of the system. System is about product and reactants. So you take the entropy change of the products minus the entropy change of the reactants. So you will get the entropy change of the system. Okay, so example for this formula. So let's say I have a reaction like this. I have CO2, which is gas, plus 3 hydrogen, become CH3OH, liquid, plus H2O, liquid. Logically, right, this reaction, the entropy change should decrease, because gas is more disordered. This is liquid. Liquid is more ordered. The arrangement of particles is more ordered, and because of that, the entropy change should decrease. Okay, should decrease. So I have information about the entropies for each substance. So the entropy for each substance is as follow. Okay, so they will give you as S theta, so which is the standard conditions. They follow the standard condition. So S theta for CO2 is positive 214. S theta for hydrogen is positive 131. S theta for methanol is positive 127. And S theta is for H2O is positive 70. Okay, so the unit for entropy is joule per Kelvin per mole. So when they say per mole, you have to be careful, So when the chemical reaction gives 3 mole, you have to times 3, Don't use 131 anymore. So use 131 times 3. Okay, use 131 times 3. And then according to the formula, we can just find out the entropy change of the system. Okay, by taking the entropy change of the products minus the entropy change of the reactants. Okay, so entropy change of the system equal to entropy change of the product minus entropy change of the reactant. Okay, so what should we do? We just add up the products. We just add up the entropies of the product. So which is 127 and 70. So we add them up minus with the entropies of the reactants. So we have 214 for carbon dioxide, 214. And then for H2, we have 3 H2, so we have to times 3 to the entropies. 3 times 131. Okay, then after that, you will get negative 410 joule per Kelvin per mole. And this should be reasonably true, like what I said. They are gas. The reaction will change it to liquid, which is more ordered. So here, the entropy change decrease. So it should be reasonable. Okay, so this is the example. So at least from here, you know how to use this formula. Okay, so now we move on. We move on to the next part. Okay, so the next part, they say next, calculate the entropy change in the surroundings. Calculate the entropy change in the surroundings. Okay, so if you want to calculate the entropy change in the surroundings, you have to take the entropy change of the this is the formula, entropy change of the surrounding. You have to use the enthalpy change of the reaction, then divide by T. Yeah? T is temperature in Kelvin. You know when they put theta, right? So when they put theta, that means standard temperature is used here, which is 25 degrees Celsius or 298 Kelvin. So that means you take the delta H reactions divide by 298, and then you get the delta S theta of the surrounding. Okay. Now, more information. If delta H theta reactions, this is enthalpy change. The unit is kilojoule per mole. This is a very normal unit, so they always use this unit, kilojoule per mole. And then change to joule by multiply with 1000. You have to change to joule because our entropy use joule, enthalpy use kilojoule. So you have to change everything to joule so that later you can get the total entropy change. So change like 1000, change to joule. Negative sign is part of the equation, and we have to always put it. Okay, so if you put negative, that means if let's say the reaction is exothermic, if it's exothermic, then exothermic itself has another negative, and then that negative will cancel off with this negative. So okay, I give you one example. So end up with it's a positive entropy. Okay, so same example again. So for this equation, okay, now we already know how to count the entropy change of the system. Okay, now I put one more information. The enthalpy change, standard enthalpy change, is minus 131 kilojoule per mole. Per mole. Okay, so if this is the information, and then let's see how we use the formula here. This second formula. Okay, so example again. Of course, my example is based on the previous one. So I can find out the delta S theta of the surrounding. So how I do it is, I take negative delta H of the reactions, divide by temperature. So delta negative, and negative is already there based on the notes here. Negative is there, always pull it. And then the delta H itself is another negative, so negative 131. So now I put negative 131. But don't forget that our enthalpy change, as in here, the enthalpy change is in kilojoule. So kilojoule, you have to multiply with 1000. Okay, so we multiply with 1000 to change it to, okay, multiply with 1000 to change it to joule, joule per mole. Okay, joule per mole. Then you have to divide by temperature, 298. You know, in terms of unit, it already matches with the unit of the entropy change. Okay, so let's say, imagine you multiply with 1000, right? You change it to joule per mole. Then you divide by the temperature, right? That is joule per mole per Kelvin. So that is the unit of the entropy change, as you can see here, joule per Kelvin per mole. So that's why you change it to joule per mole, then you divide by temperature, that is per Kelvin. So the units already match. Okay. Now, if we go and count this, then of course you will get 131 times 1000 divided by 298. You will get 4. Okay, let me write down the value first. You will get 439.6, let's say, joule per Kelvin per mole. Okay, so this is the enthalpy change of the surroundings. So it matches with the theory. Okay, as you can see, our theory just now. Okay, let's scroll up and take a look. First, our example is exothermic. So exothermic release energy to the surroundings. The surroundings will have increase in entropy. And now we look at our calculation. It is true. Exothermic entropy change of the surrounding is a positive value. That means increases the entropy change. Okay, so which is reasonable, you know. You release heat to the water, the surrounding is water, you know. Then the water have more energy, then there are more disorder. So that increase the entropy change. Okay, now next one. Use values calculated to find the total entropy change. So of course the last formula is very easy to take it. You have entropy change of the system, minus 410. You have entropy change of the surrounding, 439.6. Then now let's complete it. Okay, so now we have entropy change of the total entropy change. So that will be the entropy change of the system plus entropy change of the surrounding. Okay, the system is minus 410. The surrounding is 439.6. Then we will get 29.6, you get positive value, which is 29.6 joule per Kelvin per mole. So we get a positive value. Okay, now it means something. If delta S entropy, if the total entropy change is positive, then reaction is feasible. So feasible means possible to happen easily. So it's feasible. Okay, so which means this reaction can happen. It's feasible. Yeah. So this is all about the entropy.